So in this video, I'm going to show you how do you use the data from a mass spectrum to calculate an element's atomic mass. You're going to need a calculator, so don't just assume that I'm doing it right. I don't know why that says 14. So make sure you have a calculator so you can also practice the calculations to make sure that we're getting the same answers in this practice. Okay, so here's how we calculate the atomic mass. So we know that elements have multiple isotopes, and we know that the atomic mass is an average of those isotopes. So the way that we calculate it is we use this formula, and bring it up here. So for each isotope, so this would be for isotope 1, put it on top. Okay, so isotope 1, you would take its mass and you'd multiply by its abundance. And then if you have another isotope, you would do the same thing. So I'm going to duplicate that and just bring it over. Okay, so it's the mass times the abundance of isotope 2. And if you have more than 2 isotopes, you just keep that going. For each isotope, you do the same calculation. Now, there's only one catch to this. Abundance on these graphs is usually given to us as a percentage. Okay, and we don't want to multiply by a percentage. We want to multiply by a decimal. So how do we change from a percentage to a decimal? So let's just review that quickly. So let's say I had 92%. Okay, percent literally means per out of a cent. Cent means 100. Okay, like century is 100 years, or a penny is a cent, and there is 100 cents in a dollar. So literally what a percent means is it means that there's 92 out of 100. So we're going to be dividing that by 100. So when I do that, I have 92 divided by 100 each time. So that would equal 0.92. Okay. You can also think about it. You'll notice that the decimal place, right? If this is my decimal place, it moves over by 2. That's the effect of dividing by 100. Okay, but it is important that each time you do this, that you divide that percentage by 100 to turn it into a decimal percent. Otherwise, your atomic mass won't work. So let's look at this graph and calculate its atomic mass. So, and this is the one from the reading, from the first page. Okay, and so we already know we have 2 isotopes. We know that their masses are 10 and 11. And so we're going to use this data to calculate the atomic mass. So atomic mass is isotope 1, we'll use the 10 first. So we know that we have a mass of 10, and we're multiplying it by the percentage. And so if I look at this graph, right, the abundance, we're going to say is 20%. Okay, times 20%. And then I'm going to add it. I have another isotope, so I'm going to add it to the second one. So the mass is 11, and the percentage there is 80. Just a little trick. Your percentages must add up to 100%, right? Because, right, it's the total number of atoms. So the total number is 100%, and so you need to make sure that those 2 percentages or those 3 percentages or those 4 percentages always add up to 100%. Okay, let's change these into decimals. So we have 10 times, 20 divided by 100 is 0.2. Again, if I move that decimal place over 2 places, it gives me 0.2. Okay. Plus 11 times, I have 80%, so 80 divided by 100, that's going to give me 0.8. Okay, now I'm going to put this into my calculator. I recommend that you put it into your calculator all at once and that you use parentheses. So I'm going to put in parentheses 10 times 0.2, parentheses, plus parentheses 11 times 0.8, parentheses. And that's going to give me the atomic mass is equal to 10.8. And because we're using our units here of AMU, I can also say my unit here is AMU, atomic mass units. So what element is this? Well, this is the atomic mass of the element. So if you look on your periodic table and we find an element with an atomic mass of about 10.8, so let's see, here it is. Here's the winner, it's boron. And you'll notice that the number here is a little bit different, and that's because the numbers on the periodic table are much more precise. We use much more precise data. And so you might not get exactly the same number, but it should be pretty darn close. And it sure is. Okay, let's do another example. Okay, so here I have another example. Okay, so we're going to do the same thing. So there's two isotopes, right, because we have two peaks. So we're going to take their mass times their abundance. So the mass of the first one is 79. And its abundance, you see how it's like right above, right there? So I need to estimate approximately, so let's call it 51. Now your percentage, you might have seen that to be a little bit different. Maybe you said 52. That's okay. That's okay. You're kind of estimating here. Okay, and then the next one is a mass of 81. And its percentage, let's say, I'm going to say it's, I don't know, 58. Oops, wrong tool. Sorry, 48. Now remember that our percentages have to add up to 100. So I'm going to do a quick check and make sure that those add up to 100 before I move on. So I have 51% plus 48%. Ooh, that's not correct. That's not 100%, so I need to fix something. Okay. Maybe this one right here is actually 49%. So let me change that to 49%. So now if I do 49 plus 51, there we go, and I'm at 100%. So my percentages are good. So now I'm going to translate that into decimals. So I have 79 times, I'm going to take my decimal, I'll show you the trick here. I can take my decimal place, and I can just move it over times 2. So I'd end up with 0.51 plus 81 times, I'm going to take my decimal place and move it over 2 places. So it's going to be 0.49. And now I'm going to put it into my calculator. So here we go. I have 79 times 0.51 plus 81 times 0.49. And that's going to give me 79.98 AMU. So what element would this be? If I go back, see, 79, I found it. This one looks like it's close to 79. There it is, 79.90 compared to 79.98. That's pretty good. Again, it's not going to be exactly correct, so this element would be bromine. I'm going to show you actually one more thing. I'm going to go back up to this one. So in the reading, it talked about the most abundant isotope. So in this one, the most abundant isotope is this 11 isotope because, right, it has a higher abundance. Okay, and it also talked about how the atomic mass, because it's a weighted average, is going to be closer to that number usually. And so if we look at our answer, 10.8, it is closer to the 11 than the 10. Okay, in this one, it's pretty much closer to the 80, which is right in the middle, and that's because they're like almost exactly 50%. So usually this, like seeing kind of which one the atomic mass is closest to, is if we have pretty significant differences in the abundances of the isotopes. Okay, I have an extra practice, so feel free to do this one. Notice there's more than 2 isotopes. So I suggest that you pause and do it, and then let's see if you get the right answer. So pause it now, try it on your own, and then press play and I'll go through the answer. Okay, let's see how you did. So the first thing I did is I did my abundances. I wanted to make sure that my abundances, when I added them all up, is equal to 100%. And so this is what I got. Again, your values might change differently. As long as they're all 100% and accurate to the scale, then your number might be a little bit different, but you should still get an accurate answer. Some things that I noticed that these were at the same height, and so those percentages definitely should have been the same. Okay, so then once I have my percentages, then I can do my math. So my math looked like this. Let's try to get it to fit. Okay. And then when I did my calculation, I got that my atomic mass was equal to 72.72 AMU. And again, if you had some of your percentages slightly different, you might have gotten a very slightly different answer. And so when you look on the periodic table, what element is this? So 72.72. It looks like, I'll use a different color. It's going to be germanium, GE.